In this question, we're going to look at what happens if a ball is allowed to roll down an incline, and if it's different than if we had like a completely frictionless surface and something was going to slide down the incline. Shocking answer. The answer is, of course, it's different. How come when something rolls down an incline, it actually doesn't move quite as fast at the bottom as if it had been allowed to slide without friction? Well, it's easy to answer this from an energy perspective. Right here at the top, if we consider the center of mass of this marble to be right here, and then it's going to drop down through here, what happens is it's got gravitational potential energy at the top, but that gravitational potential energy is not just changing into the kinetic energy of this thing as the center of mass speeds up and moves down the incline, but also rotational kinetic energy as this thing goes from not rolling to rolling and rolling faster and faster and faster. So what we actually get is, if I want the speed at the bottom of the ramp here, what's the velocity at the bottom? I have to take into account the fact that this thing is not just moving translationally, but it's also rolling. And it's easy to do this with energy. So potential energy is mgh plus kinetic energy, which is 1/2, whoops, this isn't plus, this is equals, right? So the potential energy at the top is equal to the kinetic energy at the bottom, 1/2 mv squared, plus the rotational kinetic energy at the bottom, 1/2 I omega squared. And so we need the moment of inertia of the sphere, and then we can continue. So mgh equals 1/2 mv squared plus, and we're going to put the axis of rotation through the center of mass of the sphere, and so that of course means we're going to have 1/2 of 2/5 mr squared, because the moment of inertia of a sphere is 2/5 mr squared, omega squared. Now I'm going to probably change that omega in just a second, but it is worth noting that there's a mass in every quantity, so we can cancel it out, and so we have g times h equals 1/2 v squared plus 1/2 of 2/5 is 1/5 r squared, and then I have omega squared. But remember, omega is just the velocity of something divided by its radius, and so I can replace omega with v over r, and since we have omega squared, that's v squared over r squared. Well, this gets me gh equals 1/2 v squared plus 1/5 r squared cancels r squared, and so v squared. And so I have gh equals 1/2 v squared plus 1/5 v squared, which would be 5/10 plus 2/10 v squared, which is 7/10 v squared. And so if I want the final velocity of this thing, v, it's equal to 10 times 7, right? We're going to invert and multiply that fraction, times gh, and we'll square root that. So 10/7 gh is the final velocity of this thing, because when it gets to the bottom, it's not all of its energy is translational kinetic energy. Some of its energy is in fact rotational energy. Now, if we had something that wasn't rolling, but we had a completely frictionless cart or block or something that could slide this way, then we wouldn't have to worry about that, and we would just say mgh at the top equals 1/2 mv squared at the bottom, because there is no rotation. Those cancel, and we see that v is actually the square root of 2gh. Okay? These are not the same. When it's rolling, its final velocity is only 10/7 times gh. That's a little bit less, right? And it's not 14/7, it's not 2. There's a little bit less energy available for just strictly kinetic energy, because there's also some energy tied up in rotation.